Hey, all you calculus nerds out there. So kind of excited. We're starting a new unit here. This is unit 4 of my calculus program. We're going to be diving into the ideas of what a derivative does graphically. I know we've kind of already talked about that a little bit, but we're going to be looking at the graph of a function and its maximums, minimums, how it increases, decreases, its points of concavity. We're going to look at how to interpret a derivative graph and what that means for a functions graph, and the second derivative, what the second derivative does for us. So I'm really excited about how this next unit is going to play out and what it's going to look like. Stay tuned throughout the whole unit so you get the whole grasp of it. So let's go ahead and dive into our first warm-ups for lesson 4.1. Number 1 is actually a review problem from way back, and we're going to do a little bit of spiraling here because we don't want to forget about our ideas of limits. It's a good practice to keep practicing the things that we've learned in the past. So we have the limit as x approaches infinity of 2x cubed minus 3x squared plus x all over 4x cubed plus 5x minus 1. All right, so if you recall way back from unit 1 that the first method to determine a limit is to substitute, and if that produces an answer, then we're good, that's our answer. But if it doesn't produce an answer, in other words, if it ends up being indeterminate, and the different indeterminate forms, infinity over infinity, 0 over 0, 0 raised to the 0 power, infinity times 0, things like that, we have to do some algebraic manipulation with this function so that we can see what the limit of the function actually is. So if we do plug infinity in, we end up with infinity on the top over infinity on the bottom. Okay, this is by substitution. And we call that an indeterminate form. Indeterminate, okay? And because it's indeterminate, we have to do some algebraic manipulation. But if you recall, the way to deal with a limit as x is approaching infinity, the best method is to divide by the highest power. So we're going to take this and we're going to divide the top by x cubed, and we're going to divide the bottom by x cubed. So this is just my little notation here. It's not great math notation, but we're going to work with it here. So if I divide the top by x cubed, I end up with the limit as x approaches infinity. So 2x cubed divided by x cubed ends up being 2. 3x squared divided by x cubed ends up being 3 over x. And then x divided by x cubed ends up being 1 over x squared. All over. And then we divide the bottom by x cubed. So we end up with 4 plus 5 over x squared minus 1 over x cubed. And now we have a function that we can try substituting again, and this form we should be able to get an answer out of it. So if I substitute infinity in, I end up with 2 minus 3 over infinity plus 1 over infinity squared all over 4 plus 5 over infinity squared minus 1 over infinity cubed. So plugging in infinity is kind of an odd concept. So we're going to go ahead and simplify this as much as we can. If you recall, any constant number divided by infinity, what does that mean? That means any number divided by a really, really large number. Going back, the larger the denominator gets here, the smaller the number ends up being, or the closer to 0 it ends up being. So as the denominator approaches infinity, then this expression here is actually going to be approaching 0. So we can say that we have 2 minus 0, and then 1 over infinity squared. Infinity squared is infinity, so 1 over infinity is going to be 0. And then all over 4, and then that simplifies to plus 0, plus 0, not 5, minus 0. And so this ultimately simplifies to 2/4. Or we can say our answer is going to be 1/2. So that's the answer to number 1. Okay, so the limit as x approaches infinity is 1/2. Let's go ahead and take a look at number 2 now. Number 2 is a graph of a velocity function. Now we talked about the relationships between velocity and position, and this is going to actually help us as we move forward into our lessons in Unit 4, get an understanding of how things work out. But we talked about the relationship between velocity and speed. We've talked about the relationship between acceleration and velocity. We've talked about the relationship between velocity and position, or velocity and displacement. So this question is saying, when is the object slowing down? So let's try and get a visual of what that looks like. An object is slowing down. That means its speed is decreasing. Okay. Well, an object is slowing down. That depends on what direction it's going. Now, in this case, we have a velocity graph, which implies that we have a particle or something in motion that's just moving back and forth along an axis. So let's look at the different scenarios here. If I were to head in the positive direction, that would imply that my velocity is positive. So if you think of a number line here, here's 0, and I'm heading that way. I am heading in the positive direction. For me to be slowing down would imply that my velocity being positive, so I'm moving in the positive direction, I need some sort of force to cause that velocity to decrease. That velocity needs to decrease when I'm heading in this direction. Well, the force that causes my velocity to decrease is acceleration. So if velocity is positive and acceleration is kind of pushing against it, you can visualize it that way, acceleration is pushing against it, then I'm going to slow down. So if velocity is positive and acceleration is the opposite, in other words, acceleration is negative, then the particle is going to end up slowing down. Now, heading in the other direction, if I'm heading this way, then my velocity is negative. So I'm heading in the negative direction, my velocity is negative. In order for me to slow down, I would need my acceleration to be going against the direction that I'm going. So if my velocity is positive, then if my velocity is negative, then my acceleration would have to be positive to counteract that. In other words, if velocity and acceleration are opposite signs, then my particle or my object will end up slowing down. So if we look at this graph here, let's go ahead and do a quick sketch of what that graph looks like. We have the velocity graph, and we have some sort of parabolic curve there, and then we have this, and then we have a linear function on this side of things. So this is the graph, this is the axis t, this is the axis v of t. So my object is slowing down. Well, my velocity is positive in this domain, whatever this domain is. So from 0 to, it looks like on the graph, to about 4.5. So this point is 4.5 here, okay? And then my velocity is also positive from just after 8. So we're going to call this, I don't know, 8.1, just for the heck of it. That's a good number, maybe 8.2. Okay, so my velocity is positive in these two intervals here. And then this ends at 11. Okay. My velocity is positive. I am then looking for when my acceleration is negative, opposite to the velocity. Well, if my velocity is positive in this region, the acceleration, remember, is the derivative of velocity. Acceleration is the derivative of velocity. So that implies that when velocity is increasing, the acceleration is positive. And when velocity is decreasing, acceleration is negative. So let me write this down real fast. In order for my object to be slowing down, that implies that velocity and acceleration are opposite signs. Okay. Well, if we interpret this, we know that acceleration is the derivative of velocity, so we can then conclude if v of t and v prime of t are opposite signs. Okay. All right. So when is velocity and its derivative opposite signs? In other words, graphically, we're looking for when the velocity is positive and it is decreasing. Because if velocity is decreasing, then its derivative is negative. So let me write that down here. We are looking for when velocity is positive and decreasing. Okay? But if we look at it from the other side, if we look at it when velocity is negative, then it also must be increasing for our particle to be slowing down. Because again, velocity and acceleration have to be different signs. So if we look at this graph, we see that velocity is positive in this interval. When is it decreasing? When is velocity decreasing? Well, velocity is decreasing from here all the way to here. But we want to know when it's both positive and decreasing. So we're looking in this, from this point along this part of the graph to here. So this point, that point was 2. That x value or that t value was 2. So we would say the particle is slowing down over the interval 2 is less than t is less than 4.5. And where else? Let's see here. Well, over here, velocity is positive, but velocity is also increasing here, so I don't care about that region there. Where else is the sign of velocity and the sign of acceleration opposites? Well, in this region, velocity is negative, so we're looking for when velocity is increasing. Velocity is negative and increasing over this interval, starting here and going to here. So that starts at 7 there. So we would say velocity and acceleration are opposite signs from 2 to 4.5 and from 7 to 8.1 or 8.2, however we say that. So this is our answer for number 2. And our justification is because velocity is negative and increasing, or velocity is positive and decreasing, which implies that velocity and acceleration have opposite signs. All right, so I'm really excited about where this unit is headed. Stick around so you can see the lesson for 4.1 where we talk about the extreme value theorem. It'll just continue on in the next part of our playlist here.